here we go.
Hi, Henry.
Hey, Henry. Yeah, we're going to be doing some work problem today, and work problems, I should say. Work is something that you see quite a bit in physics. There is a very simple formula for it. Work is plain and simply force multiplied to distance. Force multiplied to distance. Now, the types of units you'll see would be perhaps in foot-pounds. You could have inch-pounds just as well. We could see that in a moment. If you're in the metric system, you would have a Newton meter, which you could also call a joule. And, if your force is constant, it's just about the easiest problem to work out. You just multiply a constant force over the distance that you will have it travel. That will calculate work. What makes these problems very, very interesting, though, is when force is not constant. Anybody who's ever tried to push a car that's been stranded will quickly tell you that force is not constant as you try to move it, right? I mean, once the car's moving, you're not going to be putting in as much force, right? But getting it to start moving, well, that's a whole nother issue. And, you've got plenty of problems where that's the case. Springs are a perfect example because as you're beginning to push a spring, at first maybe it doesn't seem like you're exerting much force. All of a sudden you're realizing, wait, I have to push more and more to make it move a little bit further. Same thing as stretching a spring out. Well, look, we've got a little diagram to help us see that. Suppose a force moves an object along the x-axis, along a straight line, from x equals a to x equals b, and let's slice up the distance that we're going to be moving. Slicing this up into tiny little increments is a brilliant and wonderful way to deal with this problem. So imagine that we chop up this interval from a to b into subpartitions, and you can see that between any two little x values here, like x sub 2, x sub 3, or x sub 10 and x sub 11, maybe the force moving between those two x values would be considerably different from when you began. And this is going to allow us to deal with this issue of saying, so what if the force is not constant? How on earth could we ever work out work in this regard, right? So what they're saying, the total number of work would be delta W. You could see, well, between any two subsequent x values, we could call that delta x. Well, delta x would be multiplied to whatever your force would be on that interval. And you could say, hey, add that all up. And you'd say, well, now I'd have a nice way to calculate the total force. Well, if you really think about it, look what's been highlighted right here. Delta W would be the force at some value in between there times a little distance. And imagine that we're chopping this up so that delta X gets to be super, super tiny. Well, all of a sudden, this is going to look more and more like a Riemann sum. It's going to look exactly like what we've been doing all year in calc. And you could say, well, if that's the case, then plain and simply, work would be, if we're working on this x-axis, you'd say going from x equals a to x equals b, just take this variable force, the force that's going to be changing, perhaps at every x value, perhaps, multiply it by every little tiny increment of x, delta x, add that all up. That's what a Riemann sum's really doing. That's that summation. And now you've got a way to calculate the work done. Wow. Just two little problems, but first, one of the most famous formulas in science and in math is Hooke's law. Hooke's law is applicable to springs. And Hooke's law says that the force required to stretch or compress, would you put in a little caret there, and also put in or compress. Sometimes we're only thinking about stretching a spring. This is also true if you push it in, if you compress it. But if you compress it x units beyond its natural length, you will have this formula. That force would be some constant times x. Some constant times x. So here's what we do. We're just going to do this real quick problem. Example 1, it says a force of 10 pounds is required to stretch a spring from its natural length of 8 inches to a length of 10 inches. So they're starting us off right here. A force of 10 pounds stretches from 8 inches to 10 inches. Let's just get started with Hooke's law. We're going to say f of x equals k times x. They're telling us how much force has been used. You can say plain and simply that's 10. How many units have we stretched or compressed from the natural length? 2. You see, you're going from 8 inches to 10 inches. That's going to be a stretch of 2 inches beyond its natural length. And very quickly, we can solve for k. We can divide by 2. And we'll say, well, k would equal 5. And what's going to naturally happen now is we have an equation to represent the force that would be required to compress or stretch the spring however many inches beyond its natural length we would need. So who's to say it would just be 2 inches? Maybe it would be 2.1 inches or 2.03 inches. We could figure out the amount of force needed. Well, please do this. I think this can be very helpful because when it comes to making a picture, I usually will draw this in right here and say this is the natural length that we're going to be working with. For part A, find the work done in stretching that spring from its natural length to 9 inches. Well, the natural length is 8 inches, and we'd like to stretch that out all the way out to 9 inches. Now, here's what I'd like to do. I'm going to put x equals 0 down below. Always do that for the natural length. And sometimes kids will say, why? Well, look at Hooke's law here. It's x units beyond its natural length. If you're at the natural length, you're not beyond it or short of it. You're 0 inches away from it, aren't you? And then you'd say, well, now I'm going to be 9 inches. How many inches would I be beyond that length? 1. So you could call the natural length ground 0 if you'd like. Call that x equals 0. And then you could say x equals 1. Now, according to what we see right here, guys, this is really nice. The work that you're going to do is plain and simply the integral from a to b of f of x dx. I'm going to integrate from 0 to 1. What's so super important is that we're always going to be going in regard to its natural length. You know, we're starting 0 units away from its natural length. We're going to 1 unit beyond its natural length. This is the way Hooke's law was designed to work. When you're plugging things into Hooke's law for x, it's always with the perspective of how many units beyond the natural length are we really working. And then you could say, well, what is this variable force? It's not always the same number. Well, plain and simply, it's 5x. Well, the rest of this becomes relatively simple. This becomes a fundamental theorem. What's the antiderivative of 5x? 5x squared over 2. And let's plug in our bounds from 1 to 0. Well, you plug in a 1, you'd get 5 halves. You'd get minus 0. Let's talk units. What units do you think we have here? Not foot pounds, but inch pounds. We wouldn't have joules because we weren't working in Newton meters. Everything was in the customary perspective. One more problem. One more problem. So this, in other words, is the exact same situation. And you can think, well, okay, find the work done in compressing the spring from its natural length to 7 inches. And you can think, oh my goodness. Well, here's its natural length of 8. That's x equals 0. Then all of a sudden you come here to 7 and you'd go, uh-oh, x would equal -1. Kids will go, yikes, we're going from x equals 0. We're going to push the spring in. We're going to get -1. Well, do you know what? Right now we're going to just work this out. We're going to say start at x equals 0. Go to -1. The variable force is 5x. So this is how we can deal with a compression. And, it's virtually the same problem, isn't it? You can say, well, hey, I'm going to take an antiderivative. I'm going to plug in from -1 to 0, and all of a sudden kids are probably thinking, wait a minute, you get exactly the same answer. Yeah, in this case you do. And really that's all we have for today. So if you are compressing, start off with that nice picture, draw the spring in the natural position. And then we're just going to, obviously move on the opposite direction. We'd say x equals -1.